thank you for joining us for a visit to our Civil Architectural and Environmental Engineering programs at Missouri S&T. We're in the Butler Carlton Civil Engineering Hall, and we're going to take a look at a few of the things that make our program very unique within our facilities, and also talk about what we do as a field. Overall, we have 3 degree programs: Civil, Architectural, and Environmental Engineering, and they all work together. Civil Engineering is the oldest engineering degree program on campus, hitting 150 years this year. From that, Architectural and Environmental Engineering spun out, and they're actually the 2 newest engineering degree programs on campus here at Missouri S&T, and rather unique. They're the only programs in environmental engineering or architectural engineering in Missouri as well. All 3 are the highest ranked programs for civil, architectural, and environmental engineering here in Missouri, and it's also the largest degree programs in those areas. Being a large degree program, we've got a large faculty, and we've got some excellent facilities that offer the capability to do a lot of different things. And I want to just show you a little bit of that today as we walk through the building. I wish you were here to see it in person, but since we can't do that, we'll be doing the best we can to show you some of that. And I'll also share some links to other kind of informational videos that are put together by like the American Society of Civil Engineers and other professional organizations that kind of share about the profession in a broader area. But we'll focus on what we do here at Missouri S&T and what we do really well. So let's go take a walk around the building. Thanks, and now we're into the Geotechnical Engineering Lab. And geotechnical engineering is just that, looking at geo, the earth, and how do we utilize the earth as a building material. It basically gets down to how do we support buildings, bridges, things like that overall. And to do that, we have to understand what's going on. So this is a triaxial test system. And essentially what this does is it puts pressure on soil or rock columns, and we can see the material strength and how it's going to deform under different loads as far as the building that's going to be put on it, or a roadway or a bridge. And one of the ways we do that is we can take a sample of soil. This one's actually got a coating on it that lets us look at the deformation or changes in the material under pressure. So we can put that in the pressure cell, load it up to some crazy pressures, and see how it shapes over time and might fall apart. And you can think about the Leaning Tower of Pisa. Great example, beautiful structure, great engineering, but the geotechnical aspects of it wasn't up to snuff, so it basically leans one direction. So understanding how soil works as an integral part of building systems or infrastructure systems is what geotechnical engineers do, and this is part of our labs that do that. Let's go over to the teaching laboratory and show you a little bit of a demonstration there. And this is the geotechnical teaching laboratory, so this is where the students come in as part of their class activities and get their hands dirty, literally get their hands dirty, and test the strength of soils and how soils behave under different conditions. A good example of those different conditions is earthquake. We actually have a track in earthquake engineering to understand how the earth behaves in an earthquake and how that relates to our built world, our infrastructure, our buildings, our bridges, so that we can make them earthquake resistant, or seismic resilient is another term we use for that. A good example of that is a liquefaction test. So this little example here is just a little classroom demonstration at how liquefaction of soils happens. So you can see this is kind of representing a building, and I'm pushing down on it about as hard as I can, and it's not moving. So it's nice and stable. But as soon as I put on a little bit of movement, and we'll mimic an earthquake here, we start to get some shaking, and you can see that that building isn't stable anymore. And that's a good example, but we learn about how those examples actually play out in the real world. And we have conditions where buildings actually sink down into the soil in an earthquake or tip over because of the earthquake dynamics. So now you can see that building is not stable anymore. You can understand how the soil is an integral part, or our earth, rocks, etc., is an integral part of understanding how we do built systems, our bridges, our buildings, our dams. All of that comes together and be what we do as civil engineers. So this is one other area. Let's go on and look at one more. Well, thanks for joining us now in the hydraulics laboratory. So this is the area where students learn about water flow, both in pipe systems to move throughout a city, but also natural water flow in rivers and streams and such. And we actually look at how do we engineer structures around rivers, such as bridges or embankments, to understand how it's going to resist the forces of that water. So the water table here is a good demonstration of erosion over time, and it's showing that water flowing downstream, and it's cutting into the road bank and such. And understanding how we protect bridges, roads, buildings that are near water areas or on coastal areas is really important, and it's an integral part of that. And we're seeing more and more impacts of extreme flooding conditions in the Midwest in particular, but also along coast with increased hurricane aspects. And we're also building more on the coast. So as we look to the future, understanding water, structural, and infrastructure aspects is going to be really critical. You can see how the stream bank is cutting into this and eroding down. And this is also on a larger scale how river deltas are made. All of the material that was upstream has now washed downstream, and it's changed the river flow over time. And the way that river flow is cut into the banks washed all that material down to essentially where we would deposit a delta for a river and essentially build new land area from what was eroded upstream. Dr. Wissam actually is one of our teaching assistants, and he covers our hydrology laboratory. And he's been studying this for quite some time and just finished his PhD at understanding how Missouri rivers essentially do exactly this, how they flood and how we can help protect stream banks and buildings and bridges from the effects of extreme events. So thank you very much for this stop on our visit, and now we'll be moving on to our next laboratory. And welcome. Now we're in our construction materials and testing laboratory. And this is where students actually, again, get your hands dirty and you learn how to make, test, and evaluate different types of construction materials. A couple common ones that we look at are asphalt. You can see a section here that's been rutted out over time, so we test how flexible asphalt is and different ways to make it. And concrete. And that's probably what we're best known for in our field, is the concrete materials that we develop and then essentially build those into structural elements I'll talk about in just a minute. So understanding how to make these and then the properties that you get out of them, how brittle they are, how strong they are, is really valuable when you're trying to build entire cities out of these same materials, and you throw in steel and you've basically got most of what we build out of. And we're looking at new ways to combine some of those. For example, some of our concretes, typical concretes around 3,000 or 4,000 pounds per square inch of strength. Some of our new concretes we can make up to 60,000 pounds per square inch, which essentially gives you a lot more building capacity, but also think about if you have that much energy on it and it breaks, it essentially explodes. So we understand how we go from fundamental materials properties all the way up to large built sections and how they behave when they get to failure, or when we put them into a system of what we can expect them to perform as, how much load we can put on them, and what our buildings can look like. So this is a cross section of the asphalt, and it shows how it's rutted out, and we can understand that how flexible pavements behave as a combination of the aggregate, the gray part here, and the bitumen, the black part that's put together. So we're looking at different ways to do this, and also bringing in new materials like recycled tires to improve the capabilities here and improve the sustainability of it long term as a building material. So after this one, we're going to go over to our structural testing lab and look at big systems where these are built out and where we can test them in a variety of settings. Let's move on. And welcome to one of the most exciting things going on right now. This is an active construction site, and it's actually our advanced construction and materials laboratory that's going to add about 15,000 square feet of new laboratory and learning space to our building. So it kind of combines a few different things. One is construction is a big part of our field. It's probably the most popular area where our students go into. And the construction field is understanding how to manage big projects like this one, or even much bigger, an entire skyscraper. So you're understanding how you need the right people at the site at the right time. You need the materials there. You bring together the design concepts that were put out in the original design of the building, and you make it happen. So the area of project management and construction is really one of the fastest growing areas of our field. And this is a good example of how that happens actual time, real place. And the other thing of it is this is really exciting because it's new laboratory space for us. This will be done in just a couple months, and we'll be having classes in here starting this fall. So I hope you'll be able to join us in some of that. And seeing this in person is a lot more impressive. But since it's an active construction site, we really can't go into it and test or look around much more. But I'll actually give you a link that shows a recent tour we did of this and kind of the kickoff of the project. So let's go on to the next laboratory. And welcome to our high bay structural testing laboratory. So this is an area where, when we talk about those materials, we build them into large elements, structural design elements that would be part of a building, a bridge, a dam, a roadway, and we understand how they're going to behave overall. So for example, this is a new design for mason block walls that we're going to put through an earthquake. We're actually going to put it up on the test pod over there, and we'll take it through a virtual earthquake, shaking it and putting a load on it over time, and we'll test it to failure. We'll basically just crush this and understand how it behaves. And we do that for a wide variety of different types of structural elements. We'll do large I-beams, concrete and steel, and understand how they behave under dynamic loads like an earthquake or under the static loads of being built into a building. But that understanding of how the fundamental materials work from the construction materials, and when they're cast into a large element, and when they're integrated into a building, that's really where you see structural and design elements of civil engineering taking place. And again, all of this comes together to be the field of civil engineering, but also has a lot of tie into the architectural engineering side of things also, to understand how we can build these buildings out of different materials and what they can look like, how we can shape some of the things. A really exciting area is we're actually getting into 3D printing of concrete, which is going to let us do some very interesting things that we've never done before. And that's going to be part of our advanced construction materials laboratory that we just toured a little bit ago. So let's take a look at some of the other elements in here that we test on a regular basis. And this is one of our big testing apparatus for those walls I was talking about before, but also for a large variety of things. We'll put giant bridge columns in here, but this lets us take multiple tons and put the force on the different elements at different areas. And it actually will alternate back and forth with the different pistons and essentially put an earthquake type of load on things where it's changing dynamically with time. And that lets us really test a lot of different potential scenarios that we might see out in the world, where we're going to have dynamic loads of earthquakes or wind or hurricanes, and natural hazard mitigation, or trying to mitigate hazards to building and infrastructure, is one of the things we really specialize here at Missouri S&T and we focus on. And it goes beyond just civil engineering. It really gets into the architectural side as well. So let's go look at some other things around our building. Welcome. Now we're in our architectural engineering design studio. So this is where particularly the architectural engineers look at design and look at fundamentals all the way from concepts and how we can artistically pull things out to how it's going to be physically constructed when it's actually built. And we need to understand all of that spectrum from fundamental ideas and how we can actually make them take place. So we learn everything from building and the sticks type design that you might see in a construction building or a home. And we're also looking at things, new materials like a green roof, which we'll talk about a little bit later as well. But the overall building envelope is what architectural engineering covers overall. So it gets into everything from the heating and cooling systems to smart building technologies that control lighting along with the HVAC systems and warm a building up when it's a little bit too cold before people get there, when it knows that people are coming. But also how to manage energy. So we're looking at zero energy buildings, and we'll have that as one of the videos we can link to. But zero energy buildings are where the building is generating energy through solar panels or wind and actually storing that energy for use there. And we've got 2 microgrid components on our campus where buildings actually work together to share energy as well. So in that case, we can become a lot more energy efficient and get to the part where we can use renewable energy in essentially residential homes a lot more efficiently than we can right now. So architectural engineering covers that entire building envelope, and it really starts here in the design studio where we understand those concepts and pull them all together into designs of students. Let's move on to our other studios. And welcome to our green roof facility. This is where we put a green roof. We've planted plants on top of the electrical engineering building right next to the civil engineering building. And we're learning to understand how that has a lot of benefit for building systems and for the surrounding community. It is an integral part of the building. So it does all of the functions of a normal roof of keeping the lower parts dry and giving it good insulation, but it also has the added benefit of dealing with some of the storm water. So as we've made more surfaces impervious, the water runs off quicker and leads to flooding downstream. So you can start to see how it's all connected there with understanding the building impact on the water, water impact on the buildings. And we like to see how this can manage more water. So we've actually done some research here where we've increased the water capacity. But the other side of it is, on the architectural side, it definitely brings benefit to the building. It cools the building itself, it cools the surrounding environment, and it brings basically aesthetic benefit and ecological benefit to the community as well. So when we try to tie things all together, this is a great example of that, of how civil, architectural, and environmental engineering all come together to give us the infrastructure we need and we look for. And this is part of the experience of coming to Missouri S&T, is looking at those diverse interrelationships that come together to be engineering as we know it, and specifically civil, architectural, environmental engineering. So I hope you enjoyed your tour today. This is really quintessentially what we look for our engineers, is to understand this and to bring more solutions like this to our future. Thank you. I'm glad you were able to join us for an environmental engineering program tour today. We're going to be walking through the watershed around the building of the Civil Architectural Environmental Engineering building here in Rolla, Missouri. But overall, it really represents the broader field of environmental engineering as well. We try to understand all of the natural cycles and essentially where we as humans plug into it so we can provide a happy and healthy environment to live in. And that's really important. Environmental engineering is basically about saving lives, and I'll mention a little bit about how we do that today in the case of water, and I'll relate it a little bit to air and solid waste and environmental exposure to hazardous compounds. But water is really the easiest to understand. So we're going to start today at one part of the water cycle. So as it's a cycle, it is circular and comes all the way around, but let's start with precipitation. We're not going to see any precipitation today, but if rainfall comes down here, it's going to hit a roof naturally and then shed off and quickly go into a surrounding body of water. So we will consider that, but I also want to focus in on what we're doing with the green roof here. We're trying to retain more of that water on the roof to mimic natural cycles in the water cycle, where water would fall on a vegetated area, trees or grasses, some of it would soak into the ground, and a lot of that would evapotranspire back up. And we can manage water, stormwater, in an urban setting using things like green infrastructure, such as a green roof. So the green roof here and behind me is set to absorb some of the rainfall, not all of it. So if we get a 2-inch rainfall here, a little over an inch of that is going to go through the roof and then straight to the neighboring streams, which is good. We need to keep some of that water in the surrounding streams, but not all of it, and not all of it that quickly. This also slows the water down and releases it over a longer period. And with these trays that you see in front of me, we're actually testing different media. So we've put different amendments into this that absorb more water, and now we can store an entire inch of rainfall in this 3-inch covering of the roof, and that essentially prohibits a little bit more of the rainfall flooding that we would see downstream. So we're projecting then out how this would also impact other areas. But to get to the water cycle, so some of the rain that falls on here is again stored in the soil and then used by the plants or just evaporated back up to the atmosphere, and that kind of goes back into the water cycle. It's back to where it came from. And that's more natural than all of the water sheeting off quickly off of concrete or a rubberized roof and getting downstream so fast that it doesn't have a chance to evapotranspire back up. So even right here, we're seeing a better reconnection of the urban watershed, which is really what we're shooting for, because that rainfall then is clean water for somebody else downstream or down the watershed and provides water to other people. So we'll focus on where water comes from. How we utilize that is a built infrastructure, so to say. We'll take some of that water out for drinking. We'll also use some for irrigation and some for industrial applications in a big city. But we'll focus in on the watershed. So what we're going to do then is go downstream, essentially below this building, and see where the water from this roof goes under normal conditions. So let's go down there. Welcome. We're coming on the next stage of the water cycle here in Rolla, Missouri on Missouri S&T's campus. So from the green roof that was just behind us, water that falls down gets piped down and actually enters this small urban stream. And this is not that unusual for a small urban stream. It's mostly a stormwater flow ditch for the most part. So this conveys the stormwater from the parts of Rolla to the north here, but the stormwater from the roof actually comes out a drain through here. So this really shows how it's all interconnected, that the stormwater we get in a community actually flows to this. And most cities have a very active stormwater sewer system that essentially quickly moves the water away from the city because we don't want to have flooding there. But that causes the problem downstream, and that's why we're looking at things like the green roof to slow the flow down, limit how much water enters here quickly, and also kind of purifies it. It filters it through that soil profile. So we're going to go downstream then and see where this water ends up, and then also talk about how we utilize that water as a community. Let's move downstream. So this is where the water is still coming down the little stream here right next to the civil engineering building, and it actually flows then underground. And from that, it pipes underneath part of the physics building and comes out on the other side, where it again keeps going downhill to the local lake. So let's keep moving downstream. And so the water comes back out from underground after it comes underneath the physics building, and it's still flowing downstream, and you can see that it's flowing, and it picks up a couple of other drains from around campus, from parking lots and surrounding buildings, and it keeps flowing down to this point, and down there it's going to enter another pipe system and go underground for about 1/3 of a mile to get to the local lake. And that's pretty typical. Along the way, it's picking up all of the rainfall from the parking lots and the streets and the roofs that are along the path between here and the lake. So that's how urban settings collect a lot of water very quickly, as all of those impervious surfaces are, again, tightly connected to the local hydrology, and so we see really fast fluctuations. If we had an inch of rainfall, this would be out of its banks today, and I've actually seen it to where it fills up this entire section and flows over the top of the road because the piping is too small to carry it all the time. So that's kind of how the built infrastructure relates to the natural setting, and we're again trying to understand how we can bring a little bit more nature through green infrastructure to improve water quality and urban hydrology. Well, let's go downstream to Schuman Pond, where we can see the water after it's collected. So welcome, we've reached where the water goes. This is downhill from campus and from most of the western part of Rolla, and this collects, again, the storm water from all that area, and it actually acts as part of a flood diversion, so it holds some of the water instead of rushing downstream real quickly. But it's also obviously a natural area. And you can see the plant growth is really taken over. There's a lot of nutrients that come to this, we call it eutrophication, that really impact the water quality. But now we're going to flip to the human side of it, is that we all need a lot of water. The average person in the US uses about 100 gallons of water per day when you consider all that we use for bathing, flushing toilets, for cooking, and for other things we do like laundry and dishes. So all that water has to come from somewhere. So for every community, we have to have a water supply. This is not our water supply, thankfully, because it's not in very good shape. You can see that it's pretty dirty water overall. But in some places, this may be the only water available, so we do have approaches and technologies to turn even this type of water, or even the Mississippi or Missouri River, into drinking water for a community. And we treat it very well to meet the standards for health that we have across the country. So anywhere you go in the country, if you take a drink of city municipal drinking water, it has to meet certain regulations. So we're going to teach you some of the processes to do that for even this type of water, and it's the exact same processes that are used for the Mississippi River in St. Louis to provide over 200 million gallons water capacity to about 2 million residents of that community. So we're going to grab some of the water here, right from the shore, which first of all, if we were going to get the water, we'd want to go out a little further where it's going to be a little bit cleaner, but this is all we have. So we'll take this and a little bit more water back up to the lab, where we'll then learn the process to treat it. That's where we switch over to essentially the treatment side of it. This is all the natural systems, but you can imagine if we treat our water in a certain area in different ways, allow some things not to happen in that watershed, we can actually keep the water purer. So in some cases, the first step in water purification is not letting the water get dirty in the first place.